Thank you, Robert. I hope everybody can see my screen now.
Perfect.
Thank you, Robert, for the introduction. Again, my name is Wolfgang Haderer. I'm working as a research scientist, and I'm happy to guide you through this short presentation, as also stated before, on non-destructive determination of the hardness penetration depth in thermally hardened steel parts. So first of all, what is laser ultrasound? Because this is the main technique we use here. Laser ultrasound in principle consists out of two lasers, which we can see here. One is a generation laser, and we have a second laser, a laser vibrometer, and in between there is a sample. And the generation laser is a pulsed laser normally, and it excites an ultrasonic wave, you can see here, in the sample, and the laser vibrometer detects surface vibrations again and converts it to a signal which shows the ultrasonic wave inside the material. Another possibility is the so-called pulse echo mode, which is also possible with laser ultrasound. That just means you put the generation laser and the vibrometer on the same spot on the same side of the material. We have a few advantages with a laser ultrasound, which are listed here. So clear, we are contactless. We don't need any coupling medium as it's used in traditional piezo ultrasound. We can excite high bandwidth ultrasonic waves in the material, and it's also well suited for harsh environments, for example, for hot parts in industry. What are now typical applications for laser ultrasound? This is just exemplarily here. So laser ultrasound can be used for detection of cracks and inclusions in every metals like steel or aluminum. You can see here cracks in an aluminum bar. It can also be used for grain growth measurements, for example, in dialactometers. There was a talk from my colleague Christian Kerschbaumeier before. If you're interested, watch this talk on YouTube. And it's also, of course, possible to do weld inspection with laser ultrasound. Other examples would be investigation of carbon fiber reinforced parts, for example, which are, for example, used on aeroplanes. You can see here, for example, or it's also possible to do inspection on parts of semiconductor industry, or for samples on nanoscale, like coatings or things like that. So this was just a short introduction to laser ultrasound. Now let's go to the hardness penetration depth. What does this mean, and what are standard testing methods? So first of all, what is surface hardening? Surface hardening means that, for example, on this picture you can see a crankshaft being surface hardened. So the outer surface of a steel part is heated up inductively and afterwards quenched, and so you can reach a hardened outer part of the material, while the inner core part of the crankshaft, for example, stays in its original state. This is used not only for crankshafts, but also for rails or gears, for example, in bearings and so on. The nowadays used testing standards are most of them are destructive, so we were looking for a non-destructive alternative for testing the hardness penetration depth, since this is a very interesting parameter for industry. But our method is not only limited for determining the hardness penetration depth, but it's also can be used for characterization of layered microstructures. Here you can see on the right side, you can see a micrograph of a hardened sample. This is part of a crankshaft. And you can see in the upper part here, you can see a darker region, which is the hardened layer on the outside. And this grayish kind of thing down here is the core material, which would remain unhardened. The color changes, and this brings me to this point, because while hardening, the grain structure of these steel parts change. So we get a fine grain structure in the hardened part, referred to as martensitic, and we can we stay with a coarse grain structure in the unhardened part. So how is this normally tested? So this destructive testing is done via cutting the sample, like you can see here in this picture. And let's zoom in a little bit. Then there is, for example, Vickers hardness measurements taken following a perpendicular line of from the surface, and you can see here these marks. And if the hardness reaches a predefined threshold, the hardness penetration depth is, so to say, reached. The inset shows a measurement like it's done in the normal way. So we get a hardened, so the hardness is plotted on the y-axis. We get a hardened outer layer, and following this perpendicular line, the hardness drops towards the core, and at some predefined threshold, you reach your hardness penetration depth. This is standardized in some European norm. If you're interested, this would be this norm. And of course, I have also to mention that there are other non-destructive approaches which also can determine the hardness penetration depth, like Barkhausen noise or some thermographic approaches, and of course ultrasound. So how can we, with laser ultrasound, now measure or determine this hardness penetration depth? On the right-hand side, you can see a sketch. On the upper right-hand side, there is a sketch of a sample. And again, as I said before, there is a fine core structure in the hardened outer part and a coarse grain structure in the inner unhardened part. So what we do is we take a generation laser, excite an ultrasonic wave which moves inside the sample, and we detect on the same spot with a detection laser or a vibrometer the back reflected or back scattered waves. So also from optics, it's known that waves normally are also scattered on scatterers, and we have the same here in the acoustic regime. So what happens is that ultrasonic waves propagate inside the sample and are backscattered on this grain structure. This is can also be seen here in this typical point measurement down below. But interestingly, we don't see so the amplitude is plotted on the y-axis, I have to say, and on the x-axis we can see the time of flight of the ultrasonic waves. Interestingly, we don't see any amplitude, so to say, at the beginning of the signal, and at the end of the signal we can see amplitude rising. And this is because the backscattered waves or the backscattered frequency spectrum depends on the mean diameter of the scatterer. And again, we have a fine grain structure at the beginning, or at the outer layer of the sample, sorry, because it's hardened. So we get different frequencies backscattered from the outer layer than from the inner layer of the sample. That is how we can distinguish between the two parts, hardened and unhardened. what can we do now with these signals or measurements? Again, on the left side, you can see one of these so-called A scan, which is a point measurement. With on the left side, the part with low backscattering amplitude, meaning small grains, meaning hardened layer. And on the right-hand side, you can see the part with big or more backscattering amplitude, meaning coarse grains, meaning unhardened. So if we perform now a line scan, which means taking several point measurements across the sample surface, we can move to a B scan, which is shown here, where we have the time now not on the x-axis, but on the y-axis, and the position on the sample on the x-axis. So this would be the A scan from this sample at position 15 millimeters. And what we can see here now is this grayish part down below, where we have a high backscattering amplitude, and the dark region where we have low backscattering amplitude. So yeah, and this now of course follows the edge between the two regions, unhardened and hardened and unhardened. Sorry. So the next thing we want to do is we want to make this transition between the two parts more visible. So we do some filtering and smoothing, and what we get then is from this A scan, for example, we get this step-like behavior of the signal, which helps us to distinguish again between the two parts, hardened and unhardened. So the next thing is, up to now, we only have time of flight on the x-axis. How can we now get an information of depth out of this signal? And this is done via the time of flight. So we have a longitudinal speed of sound for every material. This means the ultrasonic waves propagate with this sound. And by knowing the time of flight, we can calculate a depth information. So that's how we transfer the x-axis to a depth information. And with this step-like signal here, we can identify two interesting things, which are marked here with this green dot and this orange dot, which is kind of a which marks this transition zone between the hardened and the unhardened part. And now I want to show you. So this is the measurement at a lateral position of 13 millimeter now, and on the right hand side you can see a light microscopic image of the sample which was investigated here. And now we can, if you remember the B scan from before, you maybe recognize this this shape again here in this picture, and we can now plot these two extrema of our transition zone in this light microscopic image. And first we can see that at least the orange curve follows very nice the shape of the transition between hardened and unhardened part. I hope it's also visible on your screen, because the gray scale is not very good here. So now we have only this transition zone between the two parts, but we want to know the exact hardness penetration depth. How can we now define this threshold between the two, between the green and the orange dot. And for that, we got destructive measurements done from our company partner, which is Maschinenfabrik Alfing. And they provided us with a value of 6.7 millimeters at a lateral position of 13.5 millimeters. And we can now, so to say, calibrate our threshold to reach exactly this hardness penetration depth at this point. This was done here. And we can do a little bit of smoothing. And by doing so, we can really nice define or determine the hardness penetration depth in this sample. So this was the first approach I wanted to tell you about, but we have another approach which relies on pixel classification and machine learning. And the idea was by looking at this B-scan measurement I showed you before, it's for the human eye, it's really easy to define those two regions. And the idea was, why don't take an image analysis tool and do some pixel classification to really distinguish between the hardened and the unhardened part. And so what we did was taking an pixel classification tool, which uses supervised machine learning. It's called Elastic. And we took the B-scan, and this tool, so to say, is learning different features in this picture. So you mark a region down here as unhardened, and you mark a region at the hardened outer part as hardened. And this tool then transfers this image into a mask. And you can overlay this. This is done here. So yellow would be unhardened and blue region would be hardened. And by tracing the contour between those two parts, we can also extract something like a hardness penetration depth. This was done, and now let's have a look how well it works. So in this picture, I show you a comparison of the two methods. In red would be the pixel classification spatiotemporal. We call it spatiotemporal hardness penetration depth, and in blue, the one I showed you before, with this, so to say, with this step where we also need the destructive testing. And as you can see, in comparison, both methods really nice find this edge between the two parts, hardened and unhardened. But there is a difference in this approach with pixel classification. We did not need any calibration, because by training the algorithm properly, it finds without any calibration the border between the two regions, hardened and unhardened. So I want to show you two more examples, because of course this is a very nice example, as you can see, with nice shaped hardness penetration depth. And now I want to go some more, two more samples. One would be a sample with so-called segregations, and the other sample would be a sample with a very extended hardened layer. So first, the sample with segregations. What are segregations? For the German speakers, that would be Seigerungen, which means that the constituents of the material are kind of demixing during the production process, which leads to this grayish kind of stripes here in this picture. You might think this comes from cutting the sample, but it's not. It's really demixing of constituents. And this is now interesting when measuring the hardness penetration depth, because these segregations introduce additional scatterers. If you remember back at the second slide where I showed you this sketch of the sample structure, we have the acoustic waves backscattered from the big grains, and now we introduce additional scatterers. This can also be seen here in the B-scan, where we get some additional signal where actually there are no big grains, as you can see here in the micrograph. But when we train our algorithm to classify the pixels, it also can be found here. But if we exclude manually, in this case still this part, we can also still find the very good hardness penetration depth. And there's something popping up in the chat. Okay, sorry. The last sample I want to show you would be a sample with very extended hardened layer. So up to now, the hardness penetration depth were about 6 millimeters, 4 millimeters or something. And in this case, I want to show you a sample which is from a track wheel, where the running surface is also hardened. You can see here down below. And the hardness penetration depth reaches up to 30 millimeters. And as you can see, it's very hard to see with bare eye in the B-scan where this transition is between a hardened outer layer and the unhardened inner layer. And again, we used our pixel classification tool here. And as you can see here in this overlay, it's still possible to find the very nice transition between the two layers, also shown here in the micrograph. This brings me already to the conclusion. So I showed you a contact-free and fast determination of the hardness penetration depth via laser ultrasound. It's also possible to image different kind of heterogeneous layers. So it's not constrained to hardness penetration depth. It's also possible for other things where the grain structure changes. I showed you also a different approach which uses supervised machine learning, and as you can see, of course, we get fine, excellent results. Sorry. One thing we want to do in future is we want to connect this information now to other researchers which are working on or getting information about the grain size from these backscattering signals. And of course, we would like to do some simulations for better understanding and improve our method for thin hardening depths, meaning like below 1.5 millimeters. And if you are interested in more details, we also have a video on our YouTube page, and you can also watch this video if you're interested. And last but not least, I want to say thank you to my colleagues from RECENT, which helped me a lot. And of course to Maschinenfabrik Alfing Kessler, which provided the samples and the destructive testing. And I'm happy to answer your questions now, or you can find my address here later on.
Thank you so much, Wolfgang, for this excellent talk and overview about a hot topic and indeed a real cool topic. I always love the results here.